Okay, so let's start. So last time we saw what product of rings were, and we were analyzing ideals in product of rings after discussing a little bit about Jacobson and radical. So today we'll wrap this up with Chinese remainder theorem. So recall that if we have some commutative rings with unity R1 to Rn, then their product again with component-wise addition and multiplication is also a commutative ring with unity. And we know that so if this is this is R, then 1 of R we know what that is. This is just 1 R1. It's the n tuples of ones, yeah. So it is just ones, yeah. All ones is the multiplicative identity. So, and last time we saw that ideals in R1 cross in this product ring R1 cross R2 cross Rn are of the form I1 cross I2 cross In, where Ij is an ideal of Rj. Yeah, so the jth factor is the ideal of the jth factor of the ring. So this is special for ideals. Yeah, so you know that if if R1 to Rn were were groups, then not every subgroup doesn't look like this. Yeah, so you could have some diagonal kind of subgroup. So if you have z mod pz cross z mod pz, then you can take the subgroup generated by 1, 1 that is of order p, and then you can't write it as a subgroup in z mod pc cross some subgroup in z mod pc. Yeah, so this is special for ideals. So it doesn't happen for subgroups, or it doesn't happen for even subspaces of vector space. So it's something which is typical of ideals in product of rings. Okay, so and so this is not true for subgroups of a group or subspaces of a vector space. So, and then the plan was to discuss prime ideals in the product of rings, but we ran out of time. So, so let's start with some example. Yeah. So, for instance, in Z cross Z, so it's product of two rings. Yeah, one is Z and the other one is also Z. So, give an example of a prime ideal here.
Z cross 0.
0 cross 0, is that a prime ideal?
Z cross 0.
Z cross 0, okay. Yeah, so Z cross 0 is a prime ideal. So Z cross 0, and this is contained in Z cross Z, and you can check. So you can there are various ways of checking it. So one is to just check that if you take product of two elements lying in Z cross 0, that means the second component has the product of so if A and B are two elements in Z cross Z, such that their A times B belongs to Z cross 0. That means, so if A is, let's say, A1, A2, then A2 times and B is B1, B2, then A2 times B2 has to be 0. Yeah. So that tells you that either A2 or B2 will be 0. And that's it. That tells you that either that corresponding element, that is either A or B, belongs to Z cross 0. Yeah. So you can directly verify that this is a prime ideal. How about 0 cross 0? Is this a prime ideal?
No, sir. No.
This is not a. Why is this not a prime ideal?
So we can consider 1, 0 times 0, 1.
Yeah. So 0 cross 0 is basically the set consisting of this thing, one element. Yeah, 0, 0. So so of course 1 comma 0 times 0 comma 1 is 0 comma 0, and neither of the two belong to this. Yeah. So one has to do a little bit of work to, so it's not prime ideal cross prime ideal, because 0 is a prime ideal here, but it's not just prime ideal cross prime. So one has to think about it, what it is. Yeah. So let P contained in R be a prime ideal. So we want to categorize be a prime ideal. Then what can we say about P? Yeah. So first thing we can say, because P is an ideal, it's going to be of this form: I1 cross I2 cross I up to I. Yeah. But then one needs some restriction on ij's. Yeah. So the categorization is that ij must be equal to rj, the whole ring, for all but one subscript, some j naught. Yeah. And ij naught should be a prime ideal in rj naught. Prime ideal of rj naught. So so P is a prime ideal, then P has to have this form. Yes, and conversely. So conversely is more straightforward. So anything of this form where all the components are the full ring except one, and at that point it should be a prime ideal. These are precisely the prime ideals of R. Okay. So let's just see that these are prime ideals, and then we will see the other direction. Yeah. So the point is, one can of course do element-wise check, but one could also figure out by taking quotients. Yeah. So we know that P will be a prime ideal in R if R mod P is an integral domain. Yeah, so here you can, in this example, for instance, if you go mod the 0 ideal, you get Z cross Z, and we know that Z cross Z is not an integral domain. So there was no chance of it being a prime. Whereas if you go mod Z cross 0 in Z cross Z, then what you get is Z, which is an integral domain. Yeah. So as soon as a ring, there are two factors of two non-trivial ring factors, then it can't be an integral domain because of this kind of phenomenon, 1 comma 0 and 0 comma 1. Yeah. So that's why you need most of these factors to be ring. So let's see a proof. So conversely is easy to see, since if you take I to be R1 to Rj naught minus 1, and then Pj naught cross Rj naught R sub j naught plus 1 cross Rn, then R mod I is just Rj naught mod Pj naught, because the other factors will cancel. Yeah. Right. So just think in terms of groups. So so I mean, as a set, this quotient makes sense even as a subgroup of a abelian group. Yeah. So it's as a set, the definition doesn't differ. Only that this quotient even has a ring structure. Yeah? So this is going to be isomorphic to. So maybe I'll tell you what the map is. Yeah. And that's it. So, and this is an integral domain, so I is going to be a prime ideal. So let me just tell you what this isomorphism is. So from R, you send a map from to R. You want to give a map from R0 mod Pz not 0. So I'll give which will be an isomorphism. So first is this projection, which we called P, little p last time, yeah, in yesterday's class. So you have J naught projection onto the J naught factor. So this is a surjective ring homomorphism, yeah. And from here you also get another surjection to Rj naught mod Pj naught, which we called the quotient map, yeah. So because you are taking the quotient of this ring by this ideal. So if you compose these two ring homomorphism, you'll get a surjective. Both are surjective, yeah? So you'll get a surjective ring homomorphism. So this is your let's say theta, and what is kernel of theta? So then you can just check that kernel of theta is precisely I. So what goes to 0 under pj naught? So every factor. So R1. Um, so under pj naught, anything which is which has 0 in the j naught component will go to 0. Yeah. So maybe I'll just write kernel of. So this is not necessary, but just to analyze what we get. Kernel of pj naught is R1 rj naught minus 1, 0, and then the other factors rj naught plus 1 cross Rn. Yeah, so this is the kernel of pj naught. And but kernel of the composition theta will be slightly bigger because Q also has some kernel. So what is so we also know that kernel of theta is basically composition of these those elements under which the composition of these which map to 0 under the composition of this. Yeah. So you have to look at kernel of Q. That's going to be some subset of rj naught, and you will have to take pj naught inverse of that. That is how you get kernel of theta. If theta is the composition of these two knots, and kernel of Q is pj naught. So this is pj naught inverse of capital pj naught. Capital pj naught is this prime ideal of. And this, of course, means that in all the other factor, you can have arbitrary element of these rings, and so this is precisely I, this I. Yeah. So by first isomorphism theorem, you get this isomorphism. Okay, makes sense? So once you have this isomorphism, this is an integral domain because pj naught is a, since pj naught is a prime ideal. It's prime. Is prime in this ring rj naught. And for the forward direction, that is, every prime ideal has to look like this. That's also not same level of complexity. So of course, if P is a prime ideal, it has to look like this. Now, what does R mod P look like? And then, okay, so forward direction. So conversely, not the conversely part, but the main part. So so one can just look at, so maybe I'll just write it I equals, sorry, P equals P is a prime ideal in R, in R prime. Then and then of course we know that P is of the form I1 cross IN, IJ and RJ ideal. So we know that R1 cross, so R mod P is same as R1 cross R2. I mean R, because R is this numerator and P is this denominator, I1 cross I2 cross IN. So we could have used this as well, and this way to reduce R mod I is Rj naught mod Pj naught as well, instead of using the first isomorphism theorem. So we know that R mod P is this, and this is isomorphic to, so this is maybe you have seen it in groups. So this is R1 mod I1 plus R2 mod I2 plus Rn mod In. Yeah. So if the subgroup is of this form, then this is what you get when you take quotient. Okay. So again, if this seems a bit, so if you're not sure about this results from group theory, the way to do it is give a map from R to these quotients by sending. So let's say what this map is going to be. Yeah. So the class of R plus P is going to go to so R is going to be an element of the form R1 to Rn. It's an n tuple, right? Elements of R are n tuples. So R1 to Rn belongs to R. Then it's going to go to R1 plus I1, comma R2 plus I2. So actually you give a map from R to this guy. Yeah. But I'll just tell you what the map is. This map is. Instead of so it's the same way as we did there. Yeah. So if you want to use this method, what you'll have to do is give a map from R to this guy by sending n tuple to this thing, and then look at its kernel, and you will see that the kernel is so this is first of all going to be a surjective map, and then kernel you can check is going to be I1 cross I2 cross I1. Okay. That means kernel is going to be P. And so the induced map will be R plus P goes to this thing. So if you want to define this way, then you, without using isomorphism theorem and stuff, then you have to show that this map is well defined, because you are not using R plus P, this element. You are using a representative to define this map here, right? So that's why one has to show that this is well defined. But if you give a map from R to directly here, then you don't have to. I mean, then you are defining a map in terms of elements of R, and hence it is well defined the way you know, and then you'll have to use first isomorphism theorem to say that you get an induced map which looks like this. Okay. So this is the map, and this is the map from this to this is going to be surjective and injective, because kernel is exactly P. So this is an isomorphism, and so R mod P is isomorphic to this. So for this is going to be a prime ideal. R1 mod I1 is going to be an integral domain when. So for this to be an integral domain, all the factors except one must be 0. Yeah, because otherwise the so if is an integral is so first observation is this is not an integral domain. Integral domain if just if if there exists two ij between 1 and n, I not equal to j, such that I sub I is not equal to Ri, and I sub j is not equal to Ij. Because as soon as you have two ideals such that they are actually proper ideals, then this is not going to be integral domain, because then you can take the elements since you can take all zeros except in the ith factor, and so this maybe I will call it EI, yeah. So ith factor, and similarly EJ belongs to R. EI belongs to not R, but there's their class not in belongs to the right hand side is what one I wanted to say. belongs to R1 cross I1 to Rn cross In, and so EI bar and EJ bar will be non-zero elements, will be elements of these two rings, and their product EI bar times EJ bar is going to be 0, yeah, because I is different from J. Yeah, so this is the 0 element and hence belongs to the prime ideal P. Sorry, so why am I saying prime ideal? So this is 0, and but these two elements are non-zero. Yeah. EI bar, EJ bar is non-zero because I mean I sub I is not equal to R sub I. Yeah, so one of R sub I is not in I sub I, so it's a non-zero element of Ri mod II. And similarly, EJ is a non-zero element of so one sub Rj mod Ij, one of Rj maps to non-zero element in Rj mod Ij. Yeah. So these two are non-zero elements of this ring, but their product is 0. So this is not an integral domain. Okay, so that tells you that you can't have two factors. You should have at most one factor, which is different from Rj. So hence, I mean, so hence P is of the form I1. Hence, sorry, maybe I'll write it as the conclusion. Hence, Ij should be equal to Rj for all j between 1 and n except 1, say j naught. So this is what we can conclude, that two of them can't be a proper ideal. So at most one can be a proper ideal, and let's say that that one is Ij naught. Yeah. So once we have this, so now so now then R mod P is in that case we know that R mod P is same as Ij naught mod Ij naught, because all the other factors are the whole thing. Yeah, so it becomes just this guy, and this is an integral domain. An integral domain if and only if Ij naught is a prime ideal. Ij naught. Okay, so if P is a prime ideal, then Ij naught must be a prime ideal of Ij naught, and the other factors must be the whole ring for some j naught between 1 and n. Make sense, everyone? So this is how prime ideals look in the product of rings. So in particular, if we want to if we want to analyze this example, so maybe I'll enlarge it so that it's easier to be. So in particular, if you want to analyze this example Z cross Z, so the prime ideals of this are precisely Z cross 0 or Z cross some PZ, or it is 0 cross Z or PZ cross Z. Okay, so these are all the prime ideals in Z cross Z. So it's easy to understand what prime ideals are. As long as you know all prime ideals of each of these rings, then you know the prime ideals of the product. Okay. Any questions before we start? Before we move on? Okay, so as you can see, these elements, EIs, EJs, these, so I'm using the same notation as you see in the vector spaces. Yeah? So these are some special elements. Yeah. So we'll talk about these elements now. These are called idempotents. Okay, so maybe before I go there, I'll just make this observation. So these note. So if R is R1 cross Rn, then EIs or EJs, let's say, EJs are have the property EJs have the property that EJ square is EJ, and EI times EJ is going to be 0. Yeah, if I is not equal to. As a product of these two idempotents are in fact 1 minus EI, 1 minus EJ times EJ. This is also 0. Yeah, because so 1 is the one element of this this ring R. So 1 minus EJ times EJ is also 0. So 1 minus EJ will have 1 in all but the jth 0 in the jth component, and EJ will have 0 in every component and 1 in the jth component. So their product is 0. Okay, so these are special elements, and somehow identifying these elements help us get this decomposition of R as product. So we'll see that. Okay, so these are called idempotents. So let me just define. So, and this is the characterizing property of idempotent. This EJ square equals EJ. Okay. So I should do a little smaller. No. Okay. So idempotents. So let R be a ring. An element E of R is called an idempotent if E square equals E. Yeah. So every ring, commutative ring with unity has at least two idempotent. One is the 0. So 0 is always an idem. 0 square is 0. Yeah. And 1. These are always there. So every ring has at least two idempotent. And in fact, you can see, one can show that an integral domain can have only two idempotents, can't have more than. So that is the argument sort of given here. If it has more than two idempotent, so there exists some idempotent E, then you'll get some E and times 1 minus E will be 0. Yeah. So let E in R be an idempotent. Then first observation is that 1 minus E is also an idempotent, and the ring, you can then decompose it as product of these two rings, E times R and 1 minus E times R. Okay, so we will show that E times R is a ring, 1 minus E times R. So they are obviously ideals in R. And somehow, so if we, these are subrings of R in some generalized subring sense. So one of R will not be in E times R. So subring not in the sense that it has unity, but it's at least an ideal. But E times R has a multiplicative identity, and 1 minus E times R also has a multiplicator. So we will show that if R is a ring with commutative ring with unity, then E times R is also a commutative ring with unity. 1 minus E times R is also a commutative ring with unity, and their product is R. Okay. So that is.
Please repeat the part about subrings.
Yeah. Sure. See, we said that S is a subring of R. Um, S is a subring of R if uh, S is a subring of R, then we assumed that 1 of S equals 1 of R. Yeah. So this is when we talk about subrings of rings with unity, we make this assumption, or many books do make that assumption. So ER is contained in R. Of course, it's an ideal in R, and it satisfies all the ring axioms except this, that identity of identity of ER is not equal to multiplicative identity of ER is not equal to this. So this is the only thing which fails.
But in that class, we said that we will not use it, this convention.
We will not use this convention. So I said we'll change our convention to suit our needs. Yeah. So of course, then you can say that ER is a subring of R, but the multiplicative identity is different. Okay. So you can say that ER is a subring of R. 1 minus ER is also a subring of R. But these are also rings with unity, ER and 1 minus ER. Okay. So these are also rings with unity, and so okay, so does that clarify things?
Yes.
Okay, so that is the convention. So and then if you think of these as rings with unity, their product makes sense, and then R will be isomorphic to this product. Okay. So let's see a proof of this thing. So this is a fairly straightforward calculation that 1 minus E is idempotent. Maybe I'll we'll take a short break. Yeah, I'm getting this desperate call, so I'll just we'll
Sir,
take.
when we,
Excuse
sir,
me. Yeah.
sir, when we take the map from R to ER, then we are sending the identity of R to the identity of ER, right?
Yeah, so that map is a map of ring homomorphism, but ER is not ER as a subset of R is not going to be okay. Yeah. So if you consider ER as a subring of R, then the identity of ER doesn't go to R, the identity of R. But the projection maps are okay.
Okay.
Okay, so let me pause a bit, and we'll meet in 2 minutes. Okay. Okay, so 1 minus E whole square, if you expand it, you will get 1 minus E plus E square. Yeah, so one of the E square is same as E, so 1 minus E cancels with E square, and we get 1 minus E. So we see that 1 minus E also is an idempotent. Okay. Now we want to show that E times R is a commutative ring with unity, and then since we will use the fact that E is idempotent, that will also show that 1 minus E times R is also a commutative ring with identity, since 1 minus E is also an idempotent. Yeah, so E times R is already an ideal that we know, so we don't have to check all the ring axioms. Yeah, and the fact that it's commutative. The only thing we'll have to check is that that it has a unity. Yeah, so ER is an ideal. This is closed under addition and multiplication, and it satisfying all the ring axioms. Also, And so what is the so the point is what is going to be the unity? So E itself, so E belongs to ER, and E is the unity in ER. So E is the multiplicative identity, because if you take E times X, where X is some element of ER, then E times X is equal to X. Why? Because if X belongs to ER, X is of the form E times Y for some Y in R, and then you just multiply E times X is same as E times EY, which is E square times Y, which is same as EY, which is X. Yeah? So that tells you that E times X is equal. So we get this claim that E times R is a multiplicative ring with unity, and similarly we get one. We know that 1 minus E times R is also a commutative ring with unity. And in 1 minus E times R, the unity is 1 minus E. Yeah, so a multiplicative identity is 1 minus E. Make sense? And one other observation which I said was that if you multiply E and 1 minus E, you get 0. Yeah. So this we observed here in this thing, but meaning in this particular example here. But this is true more generally because you just expand it. Yeah. So this is just E minus E square, which of course is 0. Yeah. Because E square is same as E. So we see that the product of E times 1 minus E is 0 as soon as you assume E is idempotent. It need not be of this this particular. I mean, we are not dealing with a particular example. So now I want to give you this isomorphism. So that is the only part remaining. We want to show that R is isomorphic to ER times 1 minus ER. So I'll give you maps in both direction. So I'll give you a bijective map, and then we will check that one of these map is a ring. That's it. Yeah, so ER times 1 minus ER to R. So what is the natural map? So a typical element in ER looks like E times X for some X in R, and in 1 minus ER it looks like 1 minus E times Y for some Y in R. So the natural thing to do is add them. Yeah, so that is your map C, and get an element of R. Okay, so this is your map C. One has to check that C is a ring homomorphism and bijective. So bijective we will check by giving map in the other direction as well. So we want to give a map from R to ER times 1 minus ER. And what is the map? You take X, then E times X is in ER, and 1 minus E times X is in 1 minus ER. So this is our map phi, which again is well defined. And let's just check that the two composition, C compose phi and phi compose C are identity. So if we check this, then that will say that C and phi are inverses to each other. So what is C composed phi? So phi sends X to EX, comma 1 minus EX. And then if you apply C, it will just add these two. So if you add these two, you get 1. You get X, right? Because EX cancels out, and what you get is X. So that tells you that C composed phi is identity of R. Yeah, so just by evaluating these two maps on these elements, you can see. Similarly, phi composed C, so you take an arbitrary element EX comma 1 minus EY. So maybe here one has to so I haven't done this check. So maybe this one seems a little more complicated. So we'll do this. So C will send EX comma 1 minus EY, a general element here, to something like this. So we just have to compute what is phi of EX plus 1 minus EY. Yeah. So what is phi of EX times 1 minus EY? So you the first component will be E times this guy. Yeah. So what is E times this guy? So this is E times this element. But E times 1 minus E is 0. So what matters, what you get is E square times X, and E square is E. So you get EX, comma, and then if you multiply it by 1 minus E, then the first component goes away, and what you get is 1 minus E whole square Y. which is same as 1 minus e times y. Okay. So again, you got what you started with, ex comma 1 minus e. Yeah. So this is phi or compose C of ex comma 1 minus ey by definition, and then if you apply it, you get this guy. Yeah, so we see that the other direction, so phi compose C is also identical. So they are inverses, and then we check one of the maps. So for instance, phi we will check is a homomorphism. So phi of x plus y is just e times x plus y comma 1 minus e times x plus y, which is ex so you just expand it. So ex plus ey 1 minus e times x plus 1 minus e times y, but then you separate it out because it's component wise addition. So it's same as ex comma 1 minus ex plus ey comma 1 minus ey, which is same as vx plus vy. And similarly multiplication. Similarly, phi xy is so what is phi xy? So it's e times xy comma 1 minus e times xy, but e square is same as e. So what we can do is we can write it as ex ey, because e square is same as e, times 1 minus ex 1 minus ey, because 1 minus e is also idempotent, and this is same as ex comma 1 minus e x times so this is component wise addition, 1 minus ex 1 minus ey, component wise multiplication, which is phi x times phi y. Yeah, so we get that this is indeed a ring homomorphism, and that completes the. Okay, any questions on this this result? That once you have this idempotent, then you can split R as product of two rings. Once you have I mean, if so, you know that if E you take it to be 0, then 1 minus E is 1. Yeah, so you don't get anything non-trivial. The first factor is 0, the second factor is 1. So only if you take a non-trivial idempotent different from 0 and 1, then only you get some interesting decomposition. Okay. So this applies even for 0 and 1, but it gives you something interesting only if you take an idempotent which is different from 0 and 1. Okay. So this is product of rings is useful for what is called the Chinese remainder theorem. So let me start Chinese remainder theorem. So let me state the classical version of Chinese remainder theorem, and then maybe we'll take a break, and then we'll state the abstract version of Chinese remainder theorem. Sorry, I want to keep half of it. Yeah. Okay. So what is the classical version of Chinese remainder theorem? So I don't know if you have seen this. I hadn't seen it in my high school. I only saw it in undergraduate, but some people may have seen this in high school as well. So let n1 to nk be pairwise coprime positive integers. So the GCD of n1 and n2 is 1 is what and ni and nj is 1 if I is different from j, and let ai be some numbers between 0 and ni. So you should think of ai as remainders, yeah, when you try to divide by ni. And then there exists an integer a such that a is congruent to ai mod ni. So this is called the Chinese remainder theorem. So you can find such an a, and in fact there is you can say more. So yeah. So what can you say more? So so if you take so if you add to a product of these ni's, then that will also be a solution to this this equation. But that is the trivial part. Okay, so the non-trivial part is that you can find an a such that a is congruent to ai mod ni. Okay, for all I in 1 to k. So this Chinese, and I'm pretty sure many other places as well, but Chinese in particular used to design their calendars. Okay. So it was used to design calendars. So this is the Chinese remainder theorem. So let me just state what's the abstract version of Chinese remainder theorem, and then maybe we'll take a break. Yeah. So this have people seen this Chinese remainder theorem before? Have you guys seen this version at least? Any of you?
In Olympiad preparation, we have seen.
Yeah. So
Olympiad and essay preparation.
yeah. So that's what I guessed. So some of you may have seen it for preparations for this ISI or Olympiad exams and stuff. So there is an abstract version which will imply this. So this will be a special case of this, and this I'm sure you wouldn't have seen. Some of the so you'll see that how abstraction simplifies. So if you try to prove this directly, Chinese remainder theorem is sort of becomes a bit tedious. Yeah, so it looks a little tricky. But once you try to prove the abstract version, it won't look that tricky. Yes, I'll show you the proof today. So let R be a commutative ring with unity, and I1 to Ik be R ideals such that they are pairwise co-maximal. So this hypothesis co-prime positive integers translate to pairwise co-maximal. By the way, pairwise co-maximal means that if you take any two distinct of them, so ij comma ij prime, then the ideal generated by them is the whole ring. Yeah. So this is what co-maximal means. Pairwise co-maximal means. Yeah. So ij plus ij prime has to be whole of R for j different from j prime. So once you have that hypothesis, then first conclusion is that the intersection of these ideals is same as the product of these ideals. So when we were talking about this product, I had made this remark. Yeah. So for two ideals, so this works even for many ideals if they are pairwise. I mean, and in fact, that is how the proof will go. We'll show that product of I1 to Ik minus 1 and Ik. These are co-maximal. So we'll use induction to prove this. So we get that the intersection is same as product. So this is just in the abstract version. Okay. I mean because there is no ideal here, right? In integers, so somehow it sort of doesn't appear this part of the result. But the existence of this guy appears. So moreover, the ring homomorphism phi from this to this is surjective. So this is what is the translation of classical version in the abstract version, that the ring homomorphism, and this is not some random map. Also, I should have said the natural ring homomorphism. So what is the natural ring homomorphism? R goes to R plus I1. So same element, yeah. R plus I1. So this is different. So R is not R1 cross R1, R2 cross Rn. So there it was, Yeah, so maybe since this may be a little bit misleading. Here, this was surjective for obvious reason because so where were we doing here? Yeah. So here, because we were mapping, we were giving a surjection from product of rings to their quotients in some sense. Here, there is only one ring R, and we are taking, we are looking at various quotients of. So here we are looking at various quotients of the same ring R by different ideals. Yeah? So it is not very clear why there is going to be surjective. In fact, you need this hypothesis that these ideals are pairwise co-maximal. Otherwise, this is not true. Okay, then this is a surjective ring homomorphism, and the kernel of this ring homomorphism will be the intersection of these maximal ideals, which intersection of these ideals, which is same as the product of this ideals. Yeah, so in particular, what you get by first isomorphism theorem is that R mod this kernel is isomorphic to the target, yeah, codomain, because it's surjective. So R mod I1 intersection IK is isomorphic to. So this, by the way, is going to be same as R mod I1 to IK, because we know that the intersection is same as the product. Okay, so this is the abstract version. So I'll let you ponder about it for a little bit, and take a 5 minutes break, and then we will first show that the abstract version implies the classical version. So this you can think about it, and then we will prove the abstract version. Okay, so let's take a 5 minutes break. So you have any questions? Okay, so we saw the statement of Chinese remainder theorem, both the classical version and the abstract version. So first thing, we will show that the abstract version implies the classical version. So, okay, so save this, I haven't written it down, but so this is straightforward. So here, of course, the ring has to be Z, yeah. So, okay, I don't know where it went. This is where it went. So ring has to be Z. So so you take so assume abstract version is true. So as an application, you just take R to be Z, and I1 Ij to be the ideal generated by Nj. Yeah. So so Nj's are pairwise co-prime precisely means that so Nj's pairwise co-prime means that I mean some linear combination of Nj and Nj prime is going to be 1. Yeah, so that precisely means implies that Ij's are pairwise co-prime. I forgot to write co-prime implies that Ij's are pairwise co-maximal. Pairwise co-maximal. So that by the abstract version, we know that there is a surjective ring homomorphism from Z to Z mod N1 cross Z mod NC and NK. Yeah, nothing is moving. NK. Okay, so this is surjection by abstract version. Yeah. So in particular, if you are given these AIs, which are less than Ni and between 0 and Ni, that means you are given some representatives of elements in this ring, in these finite rings, Z mod and Nis. then you can find an integer a which will modulo ni, it will be ai. So this implies surjective. And here remember the map is n goes to, so this map is n goes to n mod n1. Yeah, that's what n plus n1z looks like, means. Yeah, so class of, so we had a better notation of this thing. The map is this class of n1, class of n in n1. Comma. This was the map. Okay, so this is surjective, precisely means classical version of Chinese remainder theorem. Okay, so we see that the abstract version, classical version, is indeed a special case of the abstract version of Chinese remainder theorem. So I hope I have unmuted. So this says that once we prove the abstract version, we'll have the classical version. And now we will see the proof of the abstract version of the Chinese remainder theorem. So we want to prove this additional identity as well, that the intersection is same as the product, and then we will prove this thing. So let's just do, let's just use induction maybe. So let's start with k equals 2. And anyway, I mean, even if you don't think of it, think of this as induction. K equals 2 is a nice case to look at. Yeah. So it will give you an idea why this is true, that R to R mod I1 cross R mod I2 is actually surjective. So this is where the crucial idea is, and then that's it. Yeah. So what do we have? We know that I1 plus I2 is R. Yeah. So that what does that mean? That means so k equals 2 means there are only two ideals, and if I1 plus I2 is R, that means we can find elements x1 in I1 and x2 in I2 such that their sum is 1. That's what this condition implies. So once we have this, so we want to show that I1 times I2 is same as I1 intersection I2. So we know that, of course, we know that I1 times I2 is contained in I1 intersection I2. That direction we already know. So we only have to show the other direction. So let's take some element x in I1 intersection I2. We want to show that this belongs to I1 times I2. So you just think of, so we will use this identity, this identity to get what we want. So x is same as 1 times x, and 1 you can write it as x1 plus x2 times x. And if you expand it, it becomes x1 times x plus x times x2 times x, which we can also write it as x times x2. Yeah, so it doesn't matter which order we write. So of course, x1 times x is going to be in I1 times I2 because x1 is in I2, x1 is in I1, and x is in both I1 and I2. Yeah, so this belongs to I1, I2, and this product also belongs to I1, I2 because x is in both I1 and I2, and x2 is in I2. So their sum is in I1, I2. Yeah. So we showed that any arbitrary element of this intersection is actually in I1, I2, assuming that the sum of these two ideals is R. Yeah, so we and the other inclusion, as I said, is always true. So we get this thing. Okay. Any questions? So that proves this this part for k equals 2, that the intersection of these ideals is same as the product. And then the second part is showing that this is surjective. Yeah. So this is where we think about it in a somewhat abstract sense. So we want to show that this map phi, which sends R to R plus I1 comma R plus I2, is surjective. So this will be surjective. So remember that there is one distinguished element 1 comma 0 and 0 comma 1. Yeah, in this right hand side. In this right hand side is 1 comma 0 and 0 comma 1, which you can think of it as 1 plus I1 comma I2 if you are using the quotient notation, and I1 uh, uh, comma 1 plus I2. So this is 1 comma 0 and this is 0 comma 1. So if we show that 1 comma 0 is in the image and 0 comma 1 is in the image, then any element here, so if x is an element, so how does a typical element here look like? So maybe I'll write it here. So so if a comma b belongs to R mod I1 plus R mod I2, then what we know is that a comma b is just a times so maybe a bar comma b bar. Yeah. So bar notation, then it is same as a times 1 0 or 1 bar 0 plus b times 0 1. So maybe put bars here. Yeah. So we are using the same bar, but of course that's why I use the quotient notation, so that is clear. So 1 bar here means in the first component means it's 1 plus I1. 1 bar in the second component means it's 1 plus I2. But from the context, it's clear where we are looking at. Yeah? So a bar comma b bar is just a times 1 bar plus, or you could have said a bar times 1, yeah, or this way. Anyway, it doesn't matter. This is same as this guy. So once you have, once you show that these elements are there in the ring, then you have that every element is there in the ring. Yeah. Every element, you can write it as something times. So basically 1 bar comma 0 and 0 bar comma 1 generate this thing. Does that make sense? Yeah. So once you have one bar comma 0 and 0 bar comma 1, you can get others by just composing, just applying phi with a and b respectively to get other. So we only have to show 2 elements are there in the image to prove surjective. Okay, so how do you show that 1 bar comma 0 is in the image? Which element will? So we have 2 elements in the ring R whose elements whose images could be these 2. So the 2 distinguished elements is x1 and x2. So you just look at x2. What is the image of x2? So phi of x2 is, so remember x1 plus x2 is 1 and x2 is in I2. So x2 is in I2 tells you that phi of x2 is x2 plus, x2 plus I1 and x2. So maybe I'll write it. Phi of x2 is x2 plus I1 comma x2 plus I2. But x2 is in I2, so this guy is just I2, and x2 x2 plus I1. This guy is also same as x1 plus x2 plus I1, right? Because x1 is already in I1. So if you change the representative by an element of I1, it won't change this element, and this is same as 1 plus I1. Okay. So we see that phi of x2 is precisely 1 plus I1 comma 1 plus I2, and similarly phi of x1 is I1 comma 1 plus I2. Okay, so we know that these guys are in the image, hence phi is surjective. Okay. Now let's do the general case. So this is the base case. Now we'll use the base case. So for the general case, I mean, one has to do the same kind of trickery, but a little more carefully, because you see we had to switch x2 and x1. Yeah, so we'll have to do let's try to do this case first. Yeah. So first observation is that claim is that I1 and I2. So now we'll do k greater equal 3. Yeah. So I2 product of Ik is R co-maximal. R co-maximal. So once we prove this, then this will, by induction, this will prove that intersection of I1 to Ik is same as the product of I1 to Ik, using this two base case. Yeah. So this will prove that so first observation is that claim implies I1 I2 Ik is same as I1 intersection. So from what we observed above for using k equals 2 case. And of course, induction tells you that the product of I2 to Ik is same as which is same as I1 intersection I2 intersection Ik. Yeah. So claim will automatically give us that condition. Yeah, so let's look at the proof of this claim. So we want to show that these two are co-maximal, and we know that I1 comma I2 and I1 comma I3 etc. are co-maximal. So we'll use that. Yeah. So I1 comma I1 plus Ij is R for all j greater equal to. Yeah. So this implies we can choose an element in I1, so let's call that xj, and an element in Ij, which is yj. So is this this xj depends upon Ij, and yj of course is in Ij, equals 1 for some xj in I1 and yj in Ij. So xj is in the first guy, yj is in the second guy, but xj, I mean, you can't find the same guy for all the ij's. Yeah, so xj will depend upon which ij you are taking. So this is what we get. So for each j we can do this. For all j greater equal to, we can do this greater than equal to 2 and up to k. So we want to show that these I1 and I2 are I2 to Ik, product of I2 to Ik are co-maximal. So what can we do? We just take the product of these kind of terms. Yeah. So x1 plus y1 times x2 plus no, not x1. It starts with 2, right? So x3 j equals 1 doesn't make sense. So x3 plus y3 xk plus yk. If you look at this product, these are all 1, so their product is also 1. Yeah. But if you expand it, what do you get? So one term you'll get is y2, y3 up to yk. And in the other terms, you'll have at least one factor of x. Yeah. Some x up, some subscript of x will come as a factor. Yeah. So, and the rest is alpha equals 1, where alpha is going to be in I1. Yeah. Because each term will have at least one x factor. and each of these x is in I1. So this whole sum is in I1. And what about this? So y2 is in I2, y3 is in I3, and so on. So this guy is in I2, ik. Okay, so we found one element in I1 and one element in this product such that their sum is 1. So that is what co-maximum is. So that hence the claim. Okay. So unfortunately, it's 12:30. So do you want me to continue, or we'll do the surjectivity next time? Okay, so maybe we'll do the surjectivity. I don't want to extend too much. Yeah. So we'll do the surjectivity of this thing, of this map phi to R mod I1 cross R mod I2 cross R mod IN next time. Okay. So we will use this co-maximality to get some distinguished element, and then we'll show that each of these EIs we can get as the image. Okay. So let's stop here. Are there any questions?